Hi everyone, so it's now time to begin the final chapter of the course, which is called General Relativity. And this topic is something that often scares people because we all know that general relativity is from the brain of Einstein. So people are a bit afraid that it's going to be very, very complicated, very, very hard to understand. And they're right to think that, okay, it is a difficult theory. But as far as the mathematics goes, we've already got pretty much everything we need in the previous chapter. And so what I'm going to do in this first video is not really get into all the mathematical machinery and how it's applied in general relativity. But in this first video, I just want to try to give you an overview with as little maths as possible of what general relativity is all about, because I think that's something that actually is not well understood. So if I was to ask you, what is general relativity all about? Okay, what is it a theory about? I would guess that you would probably say it's a theory about gravity. Yeah, general relativity, that's Einstein's theory of gravity, which is true. But that's not really all it's about. Okay, so if it was just about gravity, then it would just be called Einstein's theory of gravity. So why is it called relativity? And how does it connect back to special relativity? Okay, so special relativity is a special case of general relativity. Okay, so the theory of general relativity includes the theory of special relativity inside it. But it's not clear how they connect, maybe. Okay, so if I was to ask you what is the theory of special relativity about, you probably wouldn't think it's got anything at all to do with gravity. Okay, so if I were to ask you what is special relativity about, hopefully what you would tell me after the study that you've done of it with Dermot, hopefully you would say it's all about transformations between frames of reference. Yeah, so let's just do recap. What is special relativity about? It tells you if I have, say, a particle and I know its position or its velocity or its acceleration in one frame of reference, then special relativity tells me how to get those quantities in a different frame of reference. And you know that the name for this very special transformation is the Lorentz transformation. So say, for instance, I have one frame of reference like this. So let's just draw the Cartesian axes. So we have x, y, z. And, okay, let's just call that frame S. And then suppose we have another frame of reference, which we will call x bar, y bar, z bar. So we will call this frame S bar. And let's suppose that frame S bar is moving with a constant speed u. So let's just put a constant speed u along the positive x direction of S. So the Lorentz transformation tells me the relationship between these coordinates. So essentially it's like this: x bar is equal to gamma times x minus ut, y bar is equal to y, z bar is just equal to z, and t bar is equal to gamma times t minus ux over c squared. Okay, so that is the Lorentz transformation, which you have seen in special relativity. And here, this gamma thing, so this is gamma, it's just 1 over the square root of 1 minus u squared over c squared. And that, okay, so those equations, that's it. So that's all of special relativity in a nutshell. Okay, two frames of reference, this is how you transform between them. That's it, really. There's nothing more to special relativity than that. And these equations are for the position transformation. Okay, so just the coordinate transformations. If you want velocity or acceleration, you can differentiate them. Okay, fine. So that's how you transform between frames of reference. But there's a restriction on this. Okay, so this is why special relativity is called special, because it only works like this for transformations between certain kinds of reference frame. Okay, so the Lorentz transformation doesn't work for transformations between any two old frames of reference. It only works for transformations between inertial frames of reference. So we can say special relativity only applies to transformations between inertial reference frames. Now, we have to think back. What does that mean again? What does it mean if a frame of reference is inertial as opposed to being non-inertial? Well, essentially what it means, or well, the definition of what it means is that a frame of reference is called inertial if Newton's laws of motion, okay, so first law, second law, third law, if they apply, okay, if they're valid in the frame. So what that means is that a particle with no forces acting on it will either be at rest or move with constant velocity. Okay, that's the first law. The second law, the force on the particle is proportional to the acceleration of the particle. Okay, and the third law is valid too, so equal and opposite action and reaction. So if those three laws are valid in the frame, then your frame is said to be inertial. Okay, so how can it be then that you have a frame where the laws aren't valid? How does that happen? Basically, your frame is non-inertial if the frame itself is accelerating. Okay, so to put it simply, a non-inertial frame means the same thing as an accelerating frame. Okay, if you have an accelerating reference frame, then Newton's laws won't apply in it. Okay, maybe that's not obvious, so maybe I just need to make an example of that. So imagine I have a reference frame like this. X, Y, Z, and let's suppose that this frame is accelerating in the X direction of some other frame. Okay, so it always has to be with respect to some other frame, I guess. But let's suppose that this frame is accelerating in this direction, okay, with acceleration A, let it be a constant, with respect to some other inertial frame. And then if I have a particle, let's suppose that this particle is experiencing a force like this, and suppose the particle has mass m, and let's make the force be m times a. Okay, so what will happen to this particle? It will accelerate with the same acceleration as the frame. Okay, so we've got a frame here, it's accelerating in the x direction with acceleration a with respect to some other background inertial frame, and then I'm saying we have a particle in this frame of mass m, and let's suppose we apply a force to this particle in the x direction, which also makes the particle accelerate in the x direction, and let's specifically choose the force to be such that the acceleration of the particle matches the acceleration of the frame. Okay, so we choose the force to be m times a, where a is the acceleration of the frame. Okay, so what will happen? In this frame of reference, you have a force. Okay, so there's your F, there's your force, but in this frame, this particle appears to be at rest. Okay, so yes, the frame is accelerating, but the particle has the same acceleration, so it looks like in this frame, the particle is at rest, or possibly at a constant speed. But at any rate, in that frame, it looks like you've got a particle at rest or at a constant speed, and yet there's a non-zero force on it. So that's how, in an accelerating frame, Newton's laws don't apply. And the Lorentz transformation doesn't apply. Okay, and this is what Einstein was trying to do when he came up with the theory of general relativity. So yes, it turns out it's also about gravity, but more fundamentally, it's just about trying to free special relativity from this restriction. Okay, so special relativity, Lorentz transformation, only works for inertial frames, and in general relativity, what we're saying is, well, why should inertial frames be special? Okay, so why should the laws of physics favour inertial frames? No, that shouldn't be the case. Okay, we should be able to find laws of physics that work in every reference frame, whether they are inertial or non-inertial. And that's what general relativity attempts to do and succeeds in doing. Okay, so we get something that frees the Lorentz transformation, okay, frees up this restriction of it only working for inertial frames. But as a byproduct, you get a theory about gravity, which I will explain in my next video.